Hello, welcome to another lesson of sectoral structures theory. We are still in chapter 6 of the book. We want to talk about unitary structures today. So though we've seen these before, but we want to focus on them a little bit more. So unitary structures are or any sectoral structure of the form a to the x subscript ax. So we call it unitary because it's the same unit repeating several times. So the simplest unitary structures are the theta structures, which are made of a single unit. So for example, 3 subscript 3, like we see here, is a unitary structure. So we will say u subscript n is a unitary structure. So for example, we say 3 subscript 3 belongs to u subscript 3. So this indicates that it belongs to the unitary set of degree 3. Similarly, we've also seen the xi structures, which have the form 1 to the n subscript n. So these are made of n repeating units of each of which has a weight of 1. So the xi structures are also unitary structures. So we say xi n belongs to un. However, the ones we also want to focus on today are what we've referred to as xi star at one point earlier. But in general, they have the form a to the x. So for example, 3 to the 4th subscript 12, that's a unitary structure. 5 to the 7 subscript 35 is a unitary structure. And they basically are made of repeating units of the same weight. We need to notice an important thing here though. If an belongs to un, so if an is a unitary structure, then an must be isomorphic to a xi structure. So this is the key, really the key definition of a unitary structure. So for example, we have 5 cubed subscript 15 is a unitary structure, and it is isomorphic to the structure, to the xi structure 1 cubed subscript 3. So therefore we can say that a to the x subscript ax is isomorphic to 1 to the x subscript x. So this is the key definition of a unitary structure. Alternatively, we can express this in a different way. We can say a to the x subscript n is isomorphic to 1 to the x subscript n divided by a, such that a is a factor of n, or a divisor of n. For example, we can say that 8 to the 5th subscript 40 is isomorphic to 1 to the 5th subscript 40 divided by 8, which is 5. All right, so now we have our first set of definitions, and it's very clear now to us what a unitary structure is. So to state it one more time, the key types of unitary structures have the form n subscript n, 1 to the n subscript n, or a to the x subscript n. So these are the three main types of unitary. So now let's define what a unitary set is. So a unitary set, U subscript n, is the set of all sectoral structures of degree n that are unitary. So this would include the theta structure, or n subscript n, the xi structure, or 1 to the n subscript n. Notice that both n and 1 are divisors of n. Now what we will need to find are the rest of the divisors of n. So this would mean we would have n over d1 to the power of d1 subscript n. So remember, everything must have a degree n. And then if there's another divisor, we would say n over d2 to the power of d2 n, and so on. Let's look at an example. Let's say u6. So this would include 6 subscript 6, 1 to the 6 subscript 6, 2 to the third subscript 6, and 3 squared subscript 6. So this would be U6, or the set of unitary structures of degree 6. Now, of course, notice that each of these is isomorphic to a xi structure. So this is already a xi structure. The theta structure is isomorphic to 1 subscript 1. This is isomorphic to 1 cubed 3. And this is isomorphic to 1 squared 2. All of which are isomorphic structures. So we can say that UN is isomorphic to the set theta n, xi n, xi n over d1, xi n over d2, and so on. And of course, now we can easily figure out what the size of such a set is. Since the elements correspond perfectly, or one-to-one correspondence with the divisors of n, then we know that the magnitude or the size of u subscript n is simply the divisor function for n. So this will be a very important rule to remember, because we will build on it in the future, and we will see the divisor function appear over and over again. Let's continue. Let's look at the relationship or the application of the sigma bar function, or the partial sums function, to unitary structures. So let an belong to un, so that means it's unitary. Then we can say that sigma bar of an also is unitary. So if an is unitary, sigma bar of an will also be unitary. Here we have an is equal to a to the x subscript ax. Sigma bar of an will simply be adding each adjacent parts. So we will get 2n for each sum to the power of x minus 1. And why is it to the power of x minus 1? Because the order will be 1 less than that structure. So this brings us to an important concept also. So we've said earlier that n of a unitary structure is equal to a times x. We can also show that lambda, or the order of the unitary structure a to the x, is simply x. So the order is x and the degree is ax. Now for its sigma bar function, we get the order is 1 less than that, so x minus 1, and the degree will be 2a times x minus 1. Another way to prove that this is indeed the case, we know that for this, when we apply the sigma function, the new order is equal to 2 times n minus the outer weight. So 2 times n is 2ax, the outer weight is a plus a is 2a. We factor this out, we get 2ax minus 1. Now if we apply the sigma bar function again to an, we get 4a, because it's 2a plus 2a, to the power of x minus 2. And we can keep applying this. We get sigma bar to the power of r, so that's multiple summations of an is equal to 2 to the r times a to the power of x minus r. However, keep in mind that r cannot be, it must be less than x for this to work. So we can keep applying this as long as x is more than r. They cannot even be equal, of course, because then we get a 0. And the degree in this case is 2 to the r a times x minus r, while the order is simply x minus r. So this is the relationship. Notice also that with each application of this sigma bar function on a unitary structure, the result is also a unitary structure. Let's look at an example. We have here Bn is equal to 3 to the 4th subscript 12. Sigma bar of Bn, will be 3 plus 3 is 6. 4 minus 1 is 3, so 6 to the 6 cubed subscript 18, and we can keep applying this several times. Now let's look at some interesting properties as well. So n2 over n1. In other words, the degree of sigma bar an divided by the degree of an, which is simply n. So this gives us 2a times x minus 1 over ax. We cross out, or we cancel the a's, we get 2 times x minus 1 over x. We can solve for n2 also, and we get n2 is equal to 2n1 times x minus 1 over x. And remember, x is this, which is the order. We also can replace x with n1 divided by a, because remember, n1 is equal to a times x. So let's do that. So we get n2 is equal to 2n1 times n1 over a minus 1 divided by n1 over a. We can simplify this expression, and we basically cancel the n1 here and here. We can multiply both the numerator and denominator by a, and we get 2 times n1 minus a. So a very simplified expression. So n2, the degree after summation, can be simplified to 2 times n1 minus a. So we can also say it as the following: the degree of sigma bar an is equal to 2 times n minus a. Okay, what else can we look at? The other thing we can look at, we've seen before the diagonal function, which gives us the length of the line segment connecting the two delta joints of a sectoral structure. In the case of unitary structures, it gives us a special formula. So we can say, we saw it for the xi structure specifically, that the diagonal of a to the n subscript n is equal to 2n sine pi divided by n. We've seen this before. However, we also know that in this case, we can replace n by lambda because the degree and order are equal. And this gives us the diagonal is equal to 2 lambda sine of pi divided by lambda. And since we know that every unitary structure is isomorphic to a xi structure, and we also know that the diagonal for any two isomorphic structures is the same, it is equal. Therefore, we can figure out the diagonal of any unitary structure. So if we have a unitary structure a to the x subscript n, then the diagonal is simply 2x sine pi over x. And again, this is because it is isomorphic to a xi structure, and this is how we calculate the diagonal of the xi structure. A few more points before we're done. We said that the order of a unitary structure a to the x subscript n is equal to x. The involute of any unitary structure is equal to the unitary structure itself. So this is an important point. So this is one type of structures that are their own involute or self-involutes are unitary structures. If we want to look at the conjugates, we know that by definition the conjugate of a theta structure is its xi structure of the same degree. The conjugate of a xi is a theta. However, the conjugate of a to the x subscript n is equal to the following: 1 to the power of a minus 1, comma 2, comma 1 to the a minus 2, comma 2, and so on. Let's look at it in a more obvious way. So, let's say we have this structure here. We want to find its conjugate. All of these here are alpha joints. So we're going to change all of these to beta joints, which means basically each of these becomes its own part, except that last one, which has a beta joint. So this means we get, if this is, let's say 6 parts here, 5 of them will be converted to their own parts. So this will be 1 to the power of 5, comma, this joint turns into an alpha joint, so these are 2 sectors, 2. And then the same thing happens here, but this one has 2 beta joints. So 2 sectors are attached in this manner, and we are left with 4 alpha joints. So these 4 alpha joints will turn to betas, and they become their own parts, so this is 1 to the 4th. These 2 are joined together, it becomes a 2. And then here we are left with 5 alphas, so this becomes 1 to the 5. So this is the conjugate of 3, or what is it, 6 to the power of 3, subscript 18. So this is its conjugate. And let's double check the degree. We've got 10, 14, 16, 18. So that is correct. So in general, to get the conjugate of an alpha structure, that is a to the x subscript n, we get the following: 1 to the a minus 1, comma, 2, comma, 1 to the a minus 2, comma 2, and then this part here, we can repeat it as many interior parts as there are, and then we get the outer part again, which is 1 to the a minus 1. And then the degree stays the same as n. So how many, or what is the order of the conjugate? We know that the lambda plus lambda bar is equal to n plus 1. The order in this case of the unitary structure is x. So lambda bar will be n plus 1 minus x. Okay, so that's how we figure out the properties of the conjugate of a unitary structure. Thank you.